Okay, let's go through the GLIP paper. We will go through the paper, go through its important points, and then also implement it from scratch. So I think this is one of the important papers. It's from 2022, but it has a very nice idea of combining object detection with phrase grounding. And if you know about object detection or closed set object detection, the input to the model is an image and the output is bounding box along with the classes, right? So that is a traditional object detector. For phrase grounding, the input is an image and a phrase, and the output is the particular regions extracted from that input text in that image. And this paper, what it basically does is it combines both of these problem into one. And the idea is, if we can combine both of these problem into one, we can use much larger data set which is available especially for phrase grounding in terms of image text pairs, and we can also use it for object detection. And also it is important because it shows very nice way of how to combine these image and text modalities and how to do deep fusion in them. So this is one of the first multi-model models that we will be implementing, and after that we will be implementing much more coming in this series. Alright, so what is GLIP? So like I said, GLIP unifies object detection and phrase grounding for pre-training, and it brings two benefits. It allows GLIPs to learn from both detection and grounding data, and especially GLIP can leverage this massive image text pairs which is not available for object detectors, right? So for object detectors, the maximum number of annotated classes are like around thousands, and it's very hard to annotate, it's very time consuming, and it's also a lot of manual cost to annotate these object detection classes. And what here they did was leverage image text pairs which are much more abundant than object detection annotations. And they mention the same motivation here. If we go directly to the architecture, so this is the GLIP architecture. We have the input is this image, it goes to the visual encoder. For their case, they use this swing transformer. We also have this input prompt, text prompt. This is a bird text encoder for their case. And then it goes through this deep fusion. And what we have is, from visual encoder we have output O, which are the regions. So regions as shown here. So this is like a traditional region proposal network for object detectors. It proposes the regions. And for text encoders we have this, after tokenization we have this text embeddings P0. And we do this fusion at this layer, and then subsequently it passes through dynamic head module, which I implemented in the last video also. It's also available on my GitHub. And these text embeddings go through these BERT layers, and then do this fusion again, and it happens n times. So this is kind of a deep fusion. So there are multiple kind of fusions: early fusions, late fusions, and this intermediate fusions or deep fusions, which happen in this intermediate states, and there are many layers where it happens. So this is deep fusion, and this fusion is cross attention, across from text to image. So this is text to image and also image to text. So in both direction this fusion is happening. And finally we get, after this fusion, we have these image regions O1 to ON, and we also had these text embeddings from P1 to PM, and we find the dot product across them, and we want to maximize the dot product where the region matches the text embedding. Right, so we have this localization loss, which is for object detection, and we have this alignment loss, which is the dot product loss. How closely these text embeddings match with these regions which we are proposing. So if you remember, it and they also show it in their motivation. The GLIP does something very similar, but the difference between GLIP and this is that GLIP is on image level, right? So they have these image embeddings and text embeddings, and they'll also do this dot product correspondence, but this is on the image level, and in their case they have this on a much granular level, so object levels. Let's go directly to this unified formulation of object detection and phase grounding, and then we'll come back to also the data set that they were able to use to train this. So for typical object detection, like I mentioned, we have this image visual encoder denoted by encoder of I. It can be a CNN base or transformer base as backbone, and it extracts this region of box features O. And then each of these box feature is fed into two prediction heads. There's a box classifier C and a box aggressor R. Right. So this is traditionally for a single stage detector. We have a backbone and then we have two heads, a classifier head and a regressor head. And the total loss of the object detector is classification plus localization. And in two-stage detector, we have a separate region proposal network, which only distinguish the region based on background or foregrounds and refine their anchors and refine the bounding boxes or regions. And then those refined regions are fed into a second stage, which further classifies it into classification and localization. So this is a traditional difference between two-stage detectors versus one-stage object detectors. And this in one-stage detector, sometimes we also have this centerness loss. So for example, like for centernet for object detection. And this is the mathematical formulation. We have O coming from encoded image. So this is the backbone, CNN or swing transformer in this case. And then this O is multiplied with this weight matrix. O is of n cross D. So n are the number of regions that it is proposing. D is the dimension. W is C cross D, is the weight matrix. And the output, what we get S of class is n cross C. So n is the number of proposals and C is the number of classes. And yeah, each class can have 0 and 1, and the dimension of these targets for this loss. Mostly cross entropy loss, but it is also focal loss for single stage detector. And this is typically one hot encoded. So normally this n number of proposals are much larger than the number of targets in the image. So typically in object detectors, the typical number of targets are, I think, on average around 20, and this n is around thousands. So how do we match between more number of proposals to less number of actual targets? And it is normally done in a classical way with many to one matching. Which is based on IOU scores, or bipartite Hungarian matching, which is normally used in object detectors like TITR. And they mentioned, yeah, loss is typically cross entropy loss for two-stage or a focal loss for one-stage detector. So this is the formulation of object detectors. There's a typical formulation, and now they will basically show, which is interesting, how to formulate this object detector as a phase grounding. Right. So instead of classifying each box into C classes, they formulate detection as grounding task. And how they do this is basically given object classes, one simple way is to construct a text prompt by just appending these object classes separated by these commas, and appending also this text prompt detect. So now the input to object detection will not just be a single image, it will be an image and this text prompt. And this text prompt is basically the number of classes that we want to detect in that image, separated by commas. And they also discuss how to design this prompt, right? So certain language models prefer certain kind of prompts, and for BERT they find the kind of prompt that gives the best results is this kind of prompt. The object classes names separated by periods and a space. So we have all the classes in the image, we append the period and the space between them. And it works better than this kind of human-friendly prompt. So how to convert between object detection and grounding? So this is the same as in the previous object detection case. We have object regions proposals coming from the backbone. It is again CNN or swing transformer based backbone, and it proposes n regions. This is the new part. We have the text prompt now. For object detection, we don't have text prompt normally for typical closed set object detectors. It goes to this language encoder and we get this P. And now this S ground is the matrix multiplication of O and P transpose, right? So P has a dimension of M cross T, and M is the number of text embeddings, and D is the dimension of the of each embedding. So with P is of dimension M cross T, so M is the number of tokens and D is the embedding of each of those tokens. And they mentioned that this P in this case behaves very similarly to W in above, right? So if you go above again, so we get this S class by multiplying O with W transpose, and we are doing the same here also, O with P transpose. But P in this case is not learned weight vector, but it's coming from, it is learned, but it is coming from text embeddings. So in this way, they are able to combine object detector and phase grounding in a single framework. So again, the idea is get all the classes of an object detector and concatenate them together, separated by these periods and spaces, and pass it through a text encoder, and then multiply these two, and then you get these grounding scores. However, there is one issue though. The S grounding has dimensions of n cross m. N again is the number of object proposals and m is the number of token embeddings. And the target is of dimension n cross c. So these are different dimensions and you cannot typically do the cross entropy on these different dimensions. And why is that different, right? So we have to see. And so they give three reasons why m is different, but you can also think that this will be different, right? So the number of tokens are different, I mean. So the n is the same, but m is different from c. And the reason is some phrases contain multiple words like traffic lights. So that will be, in classical object detector, that will be only one class. But if you have this text embedding after tokenization, so this will at least be two words, traffic and light. And sometime doing this tokenization, a single word is also split it into multiple words. So like toothbrush is split it into tooth and brush. And sometimes we also add this special token like detect, and that will also increase the size of M as compared to the number of classes C. Although in our case we are not using detect, as they mentioned that this kind of prompting does not give as good results as this prompting, where we have periods separated by spaces. And finally, we also have no object token, which is added to the end of tokenization sequence. So this token indicates that there is no object present, right? So again, we have n cross m detections. N is the number of proposals, which is normally much higher. It is around thousands, and normally an image does not have thousands of objects. So we need to have some kind of no object token here also to indicate that most of these objects proposals are not an actual object. So how do they fix it then when m and c are not the same dimension? So the idea is quite simple. They expand the original target matrix n cross c to n cross m, and what they do is they make all the subwords a positive match, right? So instead of having a single class, which match with M. They expand C to M first, and then all the sub tokens which are in that M, which belongs to that class, they make it a positive match. And with this change, we have now both the target dimensions are n cross M and the output dimensions are n cross M. So now we can calculate the sigmoid loss, sigmoid focal loss basically. During the inference, they take the average token probabilities as a phase probability. With this formulation, now you know how they combine object detection as phase grounding as a single task. One thing important in their architecture is this language-aware diffusion, which is also shown here. So just go to the mathematical part of this. What it does is for each level OI/PI, so OI is the region embedding coming from the images, and PI are the text imaging coming from text encoder. They do this cross multi-head attention. So this XMHA is cross multi-head attention. So this gives from text to image and image to text attention. So this delta is then added to the original embeddings of O of I and then passed through the dynamic head module. Again, we implemented it in the last video. And for text delta, image to text, this is added to the text encodings and it becomes the next text feature for this cross attention. And this happens again L times, right? So all of this happens L time. So they also give the implementation of multi-head attention. And this is very typical multi-head attention. As you probably already know, we have these image features, we pass it through a linear layer to get the queries. Similarly, we have these text features, pass it through a linear layer to get the text queries. And then we have this attention, we have O, P, Q transpose and divided by this dimensionality of the embeddings. And then we get these attention maps, right? And we also get the value vector from text and images like this. We pass them through also the linear layer. And then text to image attention is we take the softmax of this attention here, multiply it with the value vector and pass it through a linear output layer. So typical cross attention. And for image to text attention, we have softmax of this attention transpose because now we want not text to image but image to X. We take the transpose of these attention weights, multiply it with the image values and pass it through this linear layer to make it image to text attention. And they say that this kind of diffusion brings multiple benefits. It improves the phrase grounding performance and it makes the learned visual features language aware, right? For all of this framework, I think one of the important point is for vision features to also be text aware, which typical object detectors are not, closed set object detectors. And finally, the pre-training, right? So how they do the pre-training. So we have discussed the model architecture. We also discussed why they are doing it, but now going into more of the data set part of what they are using to train this. First, the grounding data set cover a much larger vocabulary concept than exists in detection data, and this we already discussed that the largest object detection vocabulary covers no more than 2000 categories. So larger object detector data set is still confined to around 2000 categories. But with the grounding data, we can expand the vocabulary to virtually cover any kind of concept that covers in grounding captions, right? So with this image text pair, we have much larger vocabulary and much higher number of data sets. So they use a Flickr 30,000. They say it contains 44,000 unique phrases. We have VG captions, more than 100,000 unique phrases. So this is an order of magnitude larger than vocabulary of detection data. Here's an interesting part. They did not just use existing phrase grounding and object detection data. They also scaled up the detection data. And what they do is they train this teacher GLIP model with gold or human annotated detection grounding data. So all the Flickr 30,000 and BG captions and these different object detection annotations like Coco, they first use all them, which are humanly annotated, to train this teacher model. And then they use this teacher model to predict the boxes for web collected image text data, right? Uh, so now they collect all this data from the net or web and this image text data, and they predict the bounding boxes, but that data does not contains mostly these bounding boxes, right, which are needed for training a GLIP model. And they use this teacher model to predict those boxes, and they use this NLP parser to extract the noun phrases. And finally, a student model is trained with both the goal data and this generated pseudo grounding data, which is sometimes also called self-learning, right? So a teacher model is trained on goal data, which is humanly annotated mostly, and then they scrap the web and get these image text pairs and predict using this teacher on this scraped data. And the idea is why the student model, which is trained on this much larger scraped data plus humanly annotated data, will perform better than the original teacher model. And the reason is the teacher model is making educated guesses on this web scrape data. But the student model is having a supervised signal, and it is explicitly getting loss signal of what is the right prediction or not, right? So in this way, this supervised signal is much stronger than an educated guess of teacher model, and that's why it can generalize much better. Finally, transfer to the established benchmark. They show across several benchmarks that GLIP performs equally or better than its counterpart. It has to be shown that none of these models can do the zero shot detection because they are closed object detectors, right? They're not open vocabulary object detectors. And then GLIP, I think one of the most important point more than the accuracy itself is that it can do this zero shot evaluation. So how zero shot works is you give it an image and you give it the text prompt, and it will match the objects in that image with that text phrases. Okay, let's go through the code. Before going through my implementation of it, I want to show the official code. So this is the official GLIP repository. You can also go there. It's very well written. But one problem I had with it is very complex, and the reason is they have a lot of configurations. This also has GLIP version 2 implementation integrated in this GitHub repo. But for us, we just want to implement GLIP paper standalone without so much complexity of all these configurations. Right, so if you look at it, just this head implementation is like 1,000 lines. I don't normally measure the complexity of code by lines, but it shows you just this head is very complex. If we compare it with our implementation, it's much simpler, and I try to abstract away most of the complexity. In terms of backbone, I'm using Torch Vision Swing Transformer backbone. And for dynamic head, we already implemented in last video, so I'm just importing that module and using it here. So kind of hiding away the complexity of each individual module, but it still shows how everything is connected, and it stays true to the paper and spirit of GLIP. Okay, to go through our implementation, so this is the GLIP class we have in this model, this GLIP, and these are the only three files that you need, or this module is the only thing you need for this GLIP to work. And for any time we need to read this kind of torch neural network module, NN module, what I do like to do is go directly to the forward pass. This forward pass takes the images and captions and sizes, not important right now, it's just a pass through, and it goes to this backbone. and we look at to what this backbone does. This is the GLIP backbone. So again, going to the forward pass directly through this backbone, it takes this image size and captions which we are passing there. It passes these images through this function get visual features. Well, it decomposes images into tensor and mask. So the reason we have tensor and mask is we want to batch images together for efficient use of GPUs. And for that we have to pad images to make them of same size. And this mask shows the valued region of that image. And once we extract this, what happens is we go through all these features and pass X, which is the image, through these layers to kind of get a feature pyramid network. But let's go to what these features are, right? So these features are just Swin features from Swin backbone. And so again, this is from Torch Vision, and we are also using the weights of ImageNet for this backbone. These are the different channels of those feature pyramid networks. So if you remember, for feature pyramid network, we first have smaller number of channels but higher spatial dimension, and then we increase the number of channels and decrease spatial size. And then we have this feature projection module, which projects all of these these different channels into a single 256 dimension for easier fusion. What we do is we go through each level, we pass it the input through that level, get the features, and I'm just selecting 3 for feature pyramid network, 3, 5, and 7. We get that feature, we permute it to convert it into this format. We convert it into the same channel dimension like I mentioned before. We extract the feature mask, which is just the nearest neighbor interpolation, and then we just store the feature and the mask in these dictionaries, feature and mask dictionary. Right, so this is how we get the visual features. The text features we pass in captions and device, and we get to this get text features. Yeah, it passes to the bird. For padding, we have here is maximum length, and the maximum length here is the maximum query length, which we defined at 256. It is important here so we can batch all of these queries together. It's important to have all of them padded to length of 256, otherwise they will all be of different lengths, and we will not be able to efficiently batch them together. Right, so we get the text features, and then we create this dictionary and return it. It's just one way of returning it easily and easy to understand what's going on. So going back to our GLIP model, right? So where were we? We were here. We pass it to the backbone, and what we have is now the features, visual features, and the text features. If we go to the paper, so after this first one, we have this text features and we have this visual features. Now we want to do this encoding part, right? So this part, we pass it through VLFuse, we pass it through the BERT encoder, and we pass it through the dynamic head. And this is exactly what this part is doing. We do the fusion for the first layer, we pass it to the BERT layer, we pass it through the dynamic head module, and then we do the fusion again. So this part repeats again n number of times, right? And this is exactly what this is happening. So I think VLFuse layer is a bit more interesting than the other two ones. It's quite simple. The fusion again is the bidirectional attention block, the forward pass directly. One important thing is that we are using gradient checkpointing here, and if you don't know, I think PyTorch has very good documentation about it. Is what it does is trade off memory for more compute. So this is one way of using this checkpointing. You pass in the function and then you pass in all the other of the arguments. Right? So if we look into what this is just the wrapper of bidirectional attention. Right? This is NumPy multi-head cross attention module, and it does exactly what I explained here. So it implements this essentially. It passes image regions to through a linear layer, get the queries, the text through a linear layer, get the text queries, multiply them to get the attention, and it also the text features and the image features values, apply the softmax of attention and attention transpose, and finally pass it through an output layer, right? So this thing exactly does that. It passes vision or region features through the projection to get the query states. The same it does for language or text features. It reshapes it for multiplying it later on. Same it does, it gets the value for vision and language by passing through them projection layers. This is just reshaping those projected layers, and then it can multiply those two queries and key states. And it also transposes them to get the language attention weights, and it minus the max of those attention weights just to make it more stable. So this is kind of the softmax trick to minus the maximum value to keep it stable. It clamps everything between minus 50,000 to 50,000. This is because we are using mixed precision training, and they proposed that for float 16 this is a good range, and we take the softmax to get the attention weights. And this is, we also apply the text masks because we have now the text query of size 256, but the actual caption size is much smaller, so we apply the masking here. And similarly we get the outputs from vision and language. So this is kind of the delta V and delta L that we get here, and then it is multiplied with gamma like I mentioned, and then added to the original feature. So this is kind of the skip layer, and this is we're just assembling back all these features into the level back. So initially we flatten all the levels, and here we just composing all the levels back. And then finally the head layer, which is a typical RPN layer basically. So if we go to the head, and this is what the head layer needs. It needs the visual input, which are the fuse features, and the language input, which are the language features. We go to the head, and again go to the head, and we go to the forward pass of this. So we get this vision and text features from the fuse module. So this text embedding, we first normalize it. Then we pass it to this dot product projection layer, which is basically just increase the number of dimension to number of anchors into the input number of channels. And the reason is we are going to multiply it with the number of proposed regions, so it needs to be of the same dimension. Just to stabilize the training, we have this multiplication and this addition of a bias. And what we do is for each feature level, we predict the logits, we predict the bounding box, we predict the regression, and we predict the centerness. We also predict the logits, but it's not actually really used. We later on will zero out its loss, and the reason I included it because it was part of the official implementation, but I will just remove it as I get time. The most important thing which I use is the bounding box prediction, the regression prediction, and the centerness prediction. And the bounding box prediction, if we go to this bounding box, and what it does is takes the number of channels, the number of outputs and number of anchors into 4. So each anchor has 4 values that it is predicting, and number of anchors for each grid point, we are just taking 1. So this is 1 anchor per spatial point. So if the spatial size is 16 cross 16, so the number of anchors is 16 cross 16. And normally if you can also increase the number of anchors, but it also increases the computation. In the official report there's also only one anchor scale, which is 1 by 1. And it's also multiplied by the scales because each level is of different scale, so it's a good idea to also multiply it with the scale parameter, which is also a learnable parameter. And we pass these features also through the dot product projection image, right? So what we are trying to do here is we have these image features and we have these text features. We are trying to project them to the same dimensionality, so we can do this matrix multiplication. So we pass this image features through this projection layer, and then we do this matrix multiplication, which is exactly this matrix multiplication, which is projection queries which are coming from the image features multiplied with the dot product of projection of tokens. And then we append this dot product logits for each level, and we do this for each level. Finally, coming here, so after we pass it through the head, we get the logits, class logits, which again we will zero out. We don't really need them, but we can use these logits also because in the traditional object detector we have this logits signal also. So if we want to use the direct signal from object detectors, we can use it. But if we want to combine both of them into this single framework and not use it, we can also do it. And finally, we have loss calculator. So let's go to the loss. We have this GLIP loss. Let's go directly to the forward pass. We create this positive map. And this positive map is, so we have 256 dimension of text embedding, right? So, but in that 256 dimension, only some part of it is relevant class. So only those part will be 1 and the rest of them will be 0. And then we have this prepared target, which takes target bounding boxes, which we want to predict. It takes the anchors, which are generated by our anchor generator, and it takes the positive map, and it selects the right anchors based on the IOU scores, which correspond to those targets. And again, we regress directly on those anchors, right? So we map these target bounding boxes to those anchors, and same for this positive map, and then we get these labels, regression targets, and token labels. Then we can directly calculate loss on them, and this is just reshaping these bounding boxes in classes, and we concatenate all these dot product logits coming in here. So this is for each level, so we concatenate across the first dimension. Same thing we do for centerness. And then we get this token loss, right? So this token loss, if we go there, which is just sigmoid focal loss, and it also applies this text masks, right? It only applies this loss to the valid text encodings. Right, after we have this token loss, which is a sigmoid loss, then we have this centerness targets, we have this IOU loss, which is a typical object detection loss. I won't go into too much detail. What we have here essentially is we have this target bounding boxes, we assign it to the anchor boxes, and we take this assignment and we take this predicted and we logits for tokens. We have also these token labels, and we pass it to the sigmoid loss. We compute the centerness loss, and we compute this generalized IOU loss. And yeah, these are all the losses, and this class loss is multiplied by 0 because, like I mentioned, we're not using it, but we can use it if we want to use it as a traditional object detector. Right, so this is all it does. Very brief recap: it passes to the backbone, it goes to the dynamic head, it takes it to the head input, and it predicts these outputs. And this is exactly what this paper described, right? So, and for inference, if we are in the inference phase, we don't have to calculate this loss. We just pass in these values, and then we can have a look in the predictor and predictor class. So I changed this class from the official implementation, because what we want to do in practice is, again, we have text and we have the image, and we get these dot product logits. We take the sigmoid of it and we aggregate the score. So what they mentioned is also we can take the mean, max, no object, but we are taking mostly the mean by default. We take this aggregate scores, so we take the mean scores, and then we apply some kind of thresholding, right? So we only keep the classes which are whose mean value is above a certain threshold. If there are too many, so we just filter out, we take the top n. And then the final score of the classification is blocks class, which is the one we calculated here, the aggregated score multiplied by the sentinel score. So this is the final score of the object. We get the valid objects. We get the valid objects, we decode them to bring them into xy coordinates. We do some extra other post-processing, clip to image, anything which is outside the image, and we remove them. We remove small boxes, and then we also pass them select over n levels. So this is passed to the non-maximum impression. Right. So pretty standard object detectors, but the main thing is, again, how we have drive the image features, the text features, how we have concatenated, and how we have multiplied the image and text features and passed through the different losses. Fine, let's go to the data set. I think the data set part is also interesting. Right, so this is a typical loading of a data set. It loads the image, converts the bounding box to get the bounding box, convert it to XY format. The only interesting thing here is convert object detection to grounding. Right. So this is the positive map that we are using in our target losses that I showed before. So how it constructs the label from object detection, it has all the positive classes, and then it samples some of the negative classes. It sorts them, and then it creates the caption. It creates this prompt, but ideally they showed that not adding this prompt is actually better. So add task prompt, we can pass false, and then we don't have this. So this is how we build the caption. We get the class name, we get the start position, of current length of the caption starts from 0, or if we have the object detection prompt, then it starts from whatever the length of this thing is, and end position is this. It is important to keep track of this positions, because we want to create a positive map then. So all the tokens which come between start position till end position will become 1. And we just append this caption to this class name to the caption, add this period and add a space, and then in the end we just add this period. And then we have this bird tokenizer. We pass the caption through this tokenizer. And then we have this positive map, which dimension is the number of boxes, and max query length, which is 256 for us. And what happens essentially is everything in between start till end token for each class becomes 1, right? And we also normalize it, right? So we don't want a class which, like a toothbrush, has 2 tokens. So we don't want it to incur higher loss than something which has 1 token, right? So finally, the trainer. So this is the trainer. It's quite simple. It just calls the train GLIP. builds the model, builds the data set, and I created a smaller subset of Coco dataset which only has dog and cat class because yeah, the original dataset is quite huge and takes a long while to train. Since we are just testing it, I created about 5,000 images of cats and dogs dataset from this Coco dataset. I will also upload it in Google Drive and share the link in the GitHub if you want to use that dataset for just testing your model. Right, so for training we're using batch size of 2, for validation just 1. We are training it for a few 100 epochs. I mean, we are defining optimizer, scheduler, nothing fancy. We have this scaler which is for mixed precision training. So it's important to scale back the and gradients. And then yeah, it's just a standard training loop. It goes to the epochs, goes through each batch, go to the strain step, get the loss, sum the loss here, and yeah, and also log it every X number of intervals. Calculate the average training loss, step the scheduler, and save the checkpoints, right? So if we just do this Python trainer, it should just start the training, right? So yeah, so it's training. Eventually we should see this batch loss dropping considerably. Again, this we are not using this classification rows, we are using regression, centerness, and dot product of token loss. Okay, now let's come back after some time to see what the training yielded. Let's visualize some of the outputs, how they look like. So at epoch 0, before the model really started training, I also have this visualization as a part of training. So after each X number of epochs, it does some visualization to see how the detection is looking like. So initially it's all over the place. This green box is the ground truth, and yeah, we don't really need to draw 1. Of course this ground truth needs to be 1, but these predictions are the red boxes which are all over the place, right? If we just randomly select few, you can see here, well, it's not that bad, but again these yeah, scores are quite low. But after maybe like 50 epochs, if we see the detections are already quite good. So this red box again is the prediction. And for this, we can see also the model is quite confident. And again, this is on the validation data set, not training data set. So the model is learning and there are no input classes here. So it is a text prompt and it has an image and it is trying to match the objects bounding boxes to the text prompts, and that's how these classes are drawn, right? Yeah, so that's it for this GLIP paper.